Hello and welcome back to the interesting topics that we are discussing. And in our latest model that we just finished, we covered details about using KiCAD to design the filter circuit. And in that category, we recently explained you about the schematic entry and the design procedure for the filter as shown on your screen. So this is a Sallen-Key second order active low pass filter. We have covered the theory in our previous modules. So if you are coming here for the first time, we encourage you first to refer back to those modules. And in the previous module, we explained, as I said, how to put the schematic into the KiCAD software and how to make interconnection, how to define the values, and then we explained you about how we can simulate. But as soon as we approach the simulation of this circuit, we encountered an error. We got some results, but those results were not satisfactory and were not appropriate. And we stopped there. We stopped that model there. But in that model was useful to understand the theory and working principle of this circuit. We explained it in our previous model in a very detailed fashion. So refer back to that model first and then come back here to now experience and see the various analyses we are likely to perform on this circuit, because we have sorted out, we have troubleshooted the problem that we encountered, and I'm going to explain you what the problem was. So what you see here is the Sallen-Key Low-Pass filter, where we are using an operational amplifier block. The name of this block is TLV 9062. You can type this number on Google to refer to its datasheet. And from that, you will come to know that this is an operational amplifier with a certain specification about gain, bandwidth, offset voltage, minimum and maximum supply voltage rating, etc. And now we are putting this as a sub-circuit in this main circuit to design a filter, specifically the low pass. We are calling it as a low pass because we have seen the transfer function of this circuit in our previous model. So what you see, it has got two pins, that is pin number 3 and 2. Pin number 2 is connected to the output. So there is this negative feedback with the gain is equal to 1. There is a direct feedback. So this block is acting as a voltage follower or as a buffer between input of the circuit and the output. Then you have got two register R1 and R2. The values are mentioned. To the one end of the R1, we are defining the input signal, and we see that there is this capacitor right over here. And if you see that at the junction of R1 and R2, you've got this C1 right here, and one end of it is connected at the junction, other end is connected to the output. So from output, if we refer back, this low is going to the positive pin, so there is a positive feedback as well. And this is a special arrangement which makes it a Sallen-Key active second order low pass filter. So here we are applying an input signal that could be a DC voltage source, that could be a time varying voltage source, that could be a small signal AC voltage source, to carry out various types of analysis, which we are going to do one by one. Now, there is obviously, we need a power supply to be fed to this operation amplifier. So there are some details we can understand from this IC. If you look at this IC actually, then you will see, so just type this number on a Google, get a data sheet, you will see that this number is giving you a 8-pin IC, which has got two operational amplifiers inside it. So there are two modules actually. So we are using only one of it, and that part is called as U1A. This part is called as U1C, and there must be then second part as U1B. So what I want to show you, I will show you how I did that. So I will take this module from the symbol library. I clicked here and now it is loading a symbol library. We need to wait for a while, and it is now loading a footprint libraries for this particular. And once the library is opened, I will search for this part. So let me write here TLB, and you can see that I have already placed this part. That's why it got highlighted. I don't need to type the whole number. So 9062, it tells me it is a dual operational amplifier, as I said. So it means it has got two units in one single IC. And then you can see the bottom information here. There is a datasheet link here. If you click, it will take you to the manufacturer website, and there you can get all details for this specific IC. But now look at this symbol. What you see here is this is the symbol which has got two pins at the input, pin number 2 and 3, and pin number 1 is the output for this part U. But look at this arrow. I need to click here. Now, as I said, there it has got 3 units. So in KiCAD, this is the unit 1 or unit A. When I click unit B says pin 5 and pin 6 are the two inputs, positive and negative respectively. Pin 7 is the output. And finally, unit C is pin number 4 and pin number 8, which signifies the negative and the positive power supply pins to the operational amplifier unit. So exactly what I have done, I have used the part A or unit A, which is pin number 3 and 2, and 1 is the output. And I have skipped unit B, which is this one. But as you can see on the schematic, I have placed this third unit C. So this is what I did. So I just click OK for this, and this unit will be placed right over here. So I will press escape button on my keypad. So as you can see that I will press escape again to get rid of the library symbol. So you see now this pin number 8 of the IC is VDD, where the power is coming from this source, that is 2.5 volts VDD. And pin number 4 is the VSS. So VSS is also, again, this is minus 2.5. So I'm using the dual power supply here. Okay, there is a certain significance to this special symbol also. We have explained that in our previous module, so refer to that. And now this particular unit, this particular label, let me move it. It belongs to this part. So I moved it and place it here. So this is my part A. This is my part C, because that's what I want in my current circuit design. I don't want two parts. In case I want to design, let's say, high pass and low pass combined together, then I will use the part B as well. So after placing this part, I will double click here, and you see that I got some symbol properties. So this is the information about the symbols of this part, TLB9062 from the manufacturer, available in KiCAD free simulation software. So you will see that, okay, there is a reference value, there is a data sheet, manufacturer link is given, it's a dual op-amp, then there is a library of the symbol, then the name of the simulation model, then it is called as sub-circuit because we are using it as a sub-circuit in our main circuit. And look at this, the pins. Pin number 1 is the output, what you see here. And pin number 2 is the input, the negative pin. Pin number 3 is the positive input pin. Pin number 4 is VEE. So where is VEE? We'll see that here. Pin number 4 is VEE or say VSS. And pin number 8 is VCC or say VDD. Okay, depends. Once that is done, what I can do is I can click the simulation model, okay, here. So once I click the simulation model, you see that I have option of having the spice model file from the manufacturer, or I can use the built-in spice model. So built-in spice model, here I have to click and I have to look for, there is an operational amplifier model which is not available. So what I'll do is that instead of using this part, I will use the generic operational amplifier part from the library from here that we have also explained you in our previous modules. But now we are doing a real world design. That's why I am interested in having the model file from the Spice library from the manufacturer. So how do I get that? I actually use the internet and I just type the word Spice model of TLV 9062. Once I get that, so here is my Google Explorer. So what I'm interested in doing is I will just say that spice model for uh, of an TLV 9062. I need to type this, okay? So if I ask Google to search it, so you see that there is a lot of information I get. So you just click on the link. For example, I click here. There is a data sheet also available. There is a product. So it tells me it is a dual operational amplifier. Maximum supply voltage is 5.5 volt. It is a 10 megahertz operational amplifier, right? So it is a CMOS op amp. And now I have here, I have to look for spice model. The data sheet I will get also. But let's say I click here, here is the architecture. You can get all information from here also. So you can see that how we do it. Okay. So let me click here, design and development. Once I do it, I will click here, design tools and simulation. And now look at this. This is TLV 9062 SPICE model. So what I need to do, I need to click here and I have to, it is a PSpice model, which is compatible with KiCAD. And look at this, this is in the zip format. So I have to store it somewhere in some folder and then save. So it says it is already exists. Do you want to replace it? I will say no because I have done it earlier. So I will say no. But after I do that, so what I did, zip file, I unzipped it and I stored it like in this folder. So here in the download, I have got components and device models from various manufacturers. Specifically in the basic model, I have models for variety of operational amplifier. And in that, I have a model for generic op amp. And then there are these parts from the manufacturer. But look at this. This is TI072. But I am interested in this model part. So TLV 9062. So after extracting the files from this compressed zip folder, which I downloaded, I got this file, which is actually a text file. I will double click it. And now you see that this is the manufacturer part and this is the macro model I am interested in simulating my circuit. So this macro model simulated parameters are given right here. Range of parameters has been simulated. And when I call this model into KiCAD, I have to understand that this is the SPICE command. Dot subcircuit, name of the model, then the pins. Sequence is standard. First comes the positive pin, then comes the negative pin, then comes the positive supply pin, then negative supply pin, and finally is the output. Then you have this model that has been created here with the dot model syntax. Then you have got current sources, voltage sources, capacitor, resistor, dependent sources, and all sort of things are there. And you can see that. And here, that dot subcircuit model ends with the dot ends command. Then there is some extra modeling that is done by the manufacturer. You can scroll down and finally you see that this finally ends right here. So this is the model file we have got access to. And where is the directory? This PC downloads basic model, then again basic models, and then you have op amps. In your computer, after you download it from the manufacturer website, you will store it some other folder. So you have to remember your path or your directory on your computer. So right, so my directory and my path is right here. So what I'll do now, I go back to my KiCAD and I will have this model directory part, download basic models, basic model, op-amps, and this one. So how I did it, I will click here and you see now I have op-amp and this one. So this is my directory and then I said open. And once that is done, you have to not forget clicking here and then choose TLV9062. Okay, once that is done, you click OK, and then your simulation model for this part is ready. Unless you do that, you are less likely to execute your submit. Now, in our previous model, the mistake we had done is to understand now. Because in our previous model, what I did, I picked up this component from the library right here and I placed it on the screen. And then I just made the interconnection. And although I had selected the model file, like here, I specified the directory, I chose the model, and then I clicked OK. And I clicked OK here also. And everything was fine. And then I directly went for a simulator here. And I started performing various kinds of analysis, for example, time domain and AC analysis. And I ran into an error. Why? Because that I will show you in a moment. For example, I click the library again, and I am interested in this operational amplifier. So let's say I have to choose unit A, and I place it here. Okay. And then I can also have unit B, and then I can also have unit C. So you see all three parts you can place right here. But now let me just focus on only single part. Let me delete that. Once I did that, I can have this part. I can have this part instead of this part. I mean, I can have this part instead of this part. Then I click here, double click here, and now look at it. It is footprint is missing, data sheet is given there. What I'll go for simulation model. Now here, I will do that. Okay, go to spice model. I will again specify the path and I will choose the model name. I will say okay. That's good. But now look at that. Again, I click simulation model. Look at the pin assignment. Now, one thing we have to understand here, there is a pin assignment between symbol and the model. So symbol pins are what KiCAD is offering us right here. Like I said, pin number 1 here is output, 3 and 2 are inputs, positive and negative respectively. Then you have a UAB, then there are other 5 and 6 and so on. And then there is like power supply pin 8 and 4. So these are symbol pins for this part by KiCAD. And then there are pins of the model offered by the manufacturer. So look at this. So there is a mapping between the two that should be accurate and without error. Unless you do that, you will run into an error. So what are the model pins? Here, since we have provided the directory path, we have got the model information, which I just showed you through the notepad file. So you scroll it down and look at this command dot subcircuit, then the model name. First pin is positive input, second is negative input, third is VCC, fourth is PEE, and fifth pin is out. That is your model pin, right? But pin number 1 is your actually the out in the symbol, and pin number 1 is the positive input in the model. So there is a mismatch. Look at pin number 2, which is like the negative pin. What is the pin number 2 here? Is the negative pin, which looks fine. Pin number 3 is the positive pin. Pin number 3 here is the positive supply pin, actually, again a mismatch. Pin number 4 is the negative pin. And pin number 4 here is the VEE, which is correct. Pin number 5 in the symbol is the is actually what is it? Pin number 5 is the part B, for the part B actually, right? Yeah, and 6 also for the part B, and 7 is also for the part B, but 8 is our positive supply pin. Let me not confuse you. Let me show you it one by one. Um, if you see that clearly, click OK. Let me show you it in a very well fashion. So let's say I click here again, once again. Uh, Look, click assignment here. So symbol pin 1 is the output, but in the model, it is positive input, which we can see from here also, as the command says. Here is the positive input, so there is a mismatch. Pin number 2, we can see it's a symbol pin is the negative input. Here also pin number 2 is the negative input. Match, there is a match. But pin number 3 is the positive input in the symbol, but pin number 3 is the VCC. Pin number 4 is the negative input for the power supply pin. It's a negative power supply pin. But here is again a match. It's a good thing. Yeah, it's a match. But pin number 5, we don't have pin number 5 in the symbol. We don't have to care about that. Okay. But here in the model, pin number 5 is the output actually. Then pin number 6, do we use pin number 6? No. In the schematic, no. We don't care, then not connected. Pin number 7, do we have pin number 7? No, we don't care. Pin number 8 is the positive supply pin, but it is showing in the model, it is not connected. So we have to actually do this mismatch into, uh, we have to actually take care of this mismatch. So when this is, in fact, in our last module, in the previous model, this was our problem. So we forgot to have a perfect mapping of the pins between symbol and the model. So we do it now. So let's say pin number 1 is output. So I will just double click here and I will say it is my output pin. Pin number 2 is negative input. Pin number 3 is my positive input. So I will say it is model pin number 1 actually in the model. So that's what I did. Then pin number 4 is VSS or VEE, which is in the model VEE. That's correct. Pin number 5, I don't use it in the symbol. So not connected. That's correct. Pin number 6 also not connected. Pin number 7, I don't use, not connected. But pin number 8 in the symbol is my positive supply. So here, pin number 8 is the positive supply. Is pin number 3 here is the VCC. So I will go for VCC is the pin number 3. Once that is done, I can be assured that my simulations will be accurate and correct. So I will say click OK. And that's what, and then after that, I will click OK here. So I have got a very good and proper and accurate pin assignments of this one. That's what I did with this model. So after encountering an error, I troubleshoot this problem, and that's what I'm showing you here. So look at this pin function. Not here in general. Go to simulation model. I have already got the spice model. Then click pin assignment and look at this. Exactly what I did. Symbol pin 1 is the pin 5 in the model, which is the output. Let me show you. Here, pin 5 is the output in the model. So that's correct. 2 minus, 2 minus. Please, pin 3 in the symbol is pin 1 in the model, which is correct. Pin 1 in the model. Pin 4 in the symbol is the negative power supply pin. So that's pin 4, which is also correctly mapped. 5, 6, 7 not connected because I'm not using the UAB part. I'm using only UA1. Otherwise, I'll have to map this correctly as well. And pin 8 in the symbol is my positive power supply pin. So it is now pin number 3 is the VCC in the model. So that's correct mapping. Okay and okay. So that was our problem in the initially. Once that is done, I will just remove this and circuit is all set for the simulation. Before I run the simulation, I will go for electrical rule checker, perform ERC, click run. and I have got 0 errors. There are some warnings though, but I will ignore them for a moment. I'm concerned about errors now, right? So 0 errors, close. All set. Once that is done, now what you can do, just close this so that we can actually use the full area of our schematic, which is fine now. Click the simulator, and once the simulator is clicked, we are here now. The first analysis I want to do is new simulation tab, operating point analysis. I want to see how much is the current, how much is the voltage in the circuit, the total circuit, and I can get the estimate about the total power delivered by the sources and the total power absorbed by the components and the devices. The main device here is op-amp. Okay, so I can get the estimate of power consumption. So if I'm a designer and I'm doing it for a specific low power application, I can optimize the power. So I will do the operating point analysis. Once that is done, it says simulation provided no plots. Please refer to the console. Is there any problem with our simulation? We'll see that in a moment. So let me see that. Let's click the run button here. Uh, let's click the run button. Now it's done. Now look at that. I have successfully performed the analysis of my circuit, which is an operating point analysis. Now it is doing an analysis as room temperature, that is 27 degree. And now it is saying that simulation results are here. So when I see X, U1, or whenever I see X, that means these are the parameters linked to the sub-circuit. Remember, we are using op-amp as a sub-circuit. Now it says the current from the voltage source V1 is minus 530 microamp approximately. Current from the voltage source V5 is again the same. So V1 and V5, I guess they are my supply voltages. Here, let me show you. Correct. This is V1 and V5. There are some voltage supplies. So from that, we are drawing the currents of approximately minus 530 microamp. So minus 530 microamp minus. Why minus sign? Because they are delivering the current to the circuit, and circuit is absorbing or drawing the current from that. That's why whenever they are delivering, there is a minus sign, and when there's this yeah, so that's coming right here. The voltages are printed here, 2.5 volt, and here is minus 2.5 volt. And now voltage at this node, that is a minus 10 nanovolt. So that's the offset voltage actually. What is the output offset voltage? 300 microvolts. So this is a real world design actually. We are using the real part. What's the output current here available? That's like 50 femtoamp because we haven't connected the load here. And then there are these two currents here. And then you can see that the currents through the resistors also given. The current through this voltage source is like minus 500 femtoamp. That's it. So things are going here. The voltage at this node is 5 nanovolt, minus 5 nanovolt. Okay. So let's come back to our simulation window. So you see now I have got these currents here. The current through the capacitor is given. Then this is like all currents inside the sub-circuit parts, XU, all these things. Then the current through the capacitor is 0 amp. Current through the resistor R2 is 500 femtoamp. Current through voltage source V4, which is our input signal source, 500 femtoamp. Current through R1 is 500 femtoamp negative. Scroll it down. So the most important information is power of the voltage source V4. V4 is our input signal source actually, so it's a 0 watt obviously. But the power dissipated in the resistors is 2.5 femtowatt. Power dissipated in R2 also 2.5 femtowatt, pretty low actually. Power consumption of the capacitor is 3 femtowatt. Now look at this. Output voltage is like 300 microvolts. That's the output offset voltage. Without any input, you still have got any output in the op amp. So that's the offset. Look at this power consumption of XU1. That is the total power consumption of your op amp is just 2.69 milliwatt. It's a quite a low power. Very good. So I'm happy with that. So I can design the low pass filter with like 0.6 milliwatt power consumption. Then there are these voltages inside the all parts of the sub circuits XU. I'm not interested in that because I'm just interested in the total power consumed by the circuit. And that's it. So I'm scrolling it down, but look at this power consumption of capacitor C2 again 10 to watt minus 1.5. So ignore. Now voltage source VDD is 2.5 volt. Voltage power consumption of this voltage source, which is 2.5 volt, is like minus 1.34 milliwatt, and V5 because the 2.5 volt for VSS as well. So it is minus 1.3 milliwatt. So total power consumption is like 2.56, what we just got here. Okay, so we are successfully done with the DC operating point analysis. That gives you understanding about the voltages and the currents in the circuit. Next, we move to time domain simulation. Let me do it. Let's say I want to apply a time state about 1 micron. Final time is like 10 milli, and I leave it optional. Click OK. Now the plot is screen is ready to get some results here. The only option is I have to press this simulation button. Before that, I want to show you this here. Is a voltage source. As I said, I have set amplitude of this voltage source to be 100 millivolt peak at a frequency of 1 kilohertz. Before that, I would be interested in, since this is a low pass filter, as I explained in the previous model, I want to see the AC analysis or body plot of it to see the cutoff frequency. But I have done that, and the cutoff frequency is about 10 kilohertz. So I will show you in a moment. So that's why I can say that 1 kilohertz signal will be filtered out. So 100 millivolt peak value of the sinusoidal signal, frequency of 1K. How I do that? I just double click this, and here I specify or change those parameters. So just click OK. Once that is done, go to simulator. You are all set. All these signals are ready to be plotted. But before that, I want to click the run simulation. Look, transient analysis is finished. Now it's like voltage versus time. What I'm interested in, V of V in. I'm interested in seeing the input signal. I've got this beautiful waveform starting from 0 going to 100 millivolt peak. Frequency of this signal is 1 kilohertz. You can measure it because I have got a cursor. So I click here cursor 1, then I click here cursor 2. So when I have the cursor 1 and 2, I have got information about the time and the voltage level. So what I do on the screen, take this cursor to the peak value right here approximately, and take the cursor to the peak value here approximately, peak to peak. So one cycle, okay, from this to this, not really, this here, here. This is second. Am I doing it properly? Time. No, 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 no. Is here also. Yeah, only here only. So you see from this time this time instant to this time instant, I have got one cycle. Okay, from peak to peak. So here I see that the V in cursor 1 and then the V cursor 2, there is a time uh, instance. The voltage is 100 millivolt each, and the total time between the two, V in 2 minus 1 is 1 millisecond. So total time is 1 millisecond, 1 over T, that is 1 over this 1 millisecond is 1 kilohertz. What is the frequency we have set? And the voltage is like, well, Obviously the voltage will be 0 because 100 minus 100 is all this one. But that's what not we are interested. We are interested in the peak value of cursor. One is 100 millivolt. Peak value of cursor is also closely 100 millivolt. So that's it. Now, next I want to see VO. So look at this. I have a gain of 1 because input and output closely. Little bit phase difference between input and output. Okay, so this signal is being filtered properly. This is not amplifier, this is a filter with a gain of 1 because in the schematic you see we have used the op-amp as a buffer voltage follower. We can use it gain if we just configured in a non-inverting configuration, have a registers to set the non-inverting gain, and we can get the gain in the filter as well, depends of your requirement. So what I'll do, I will just zoom in this portion to show you there is a phase shift, little bit phase shift. Once I right click, fit on the screen. So that's it. Very good time domain waveform. What you can do is file, export current plot as PNG, and then say save in the download folder. Let's say it is like XYZ or whatever. And then click save. So that's it. You have managed in a very good way the time domain simulation. So what you can do next is like want to see the FFT, let's say FFT of output and let's say input, whether it gives me that. So we'll see that. Run it. We'll see now. Very good. So this is output and input FFT plots. So you see now you've got the frequency at 1 kilohertz. So we have also explained you how to do FFT in our previous model. So refer to those plots. Again, get the file, export current plot as CNG. You can also do it in a way. So let's say like whatever the name you want. Save it in the download folder. That's good. Next, let us run the AC analysis now. So I click AC analysis, number of points I want like 1000, start frequency, let's say 1, which is close to DC, then 10 mega, 10 to the power 6. Click OK. I am done. Then I click run simulation. Once that is done, I am interested in plotting the gain and the phase of the output. So it is the Bode plot. Look at this beautiful waveform. The gain is 0 dBV. It's constant up to frequency of about 10 kilohertz. And that's your cutoff frequency. So which separates the pass band and the stop band in the low pass one. Okay. So you have got this. Then you have phase. And look at the phase also on the y-axis starts from 0. So it remains constant up to this frequency, like because there are capacitors up to less than 1 kilohertz is constant to 0, but then total phase shift is about minus 180 degree, right? And that's what you expect. Okay, so you can change the color also. Let's say you have this color, the blue one, say okay. And now this is your nice plot. Again, click the file, export current plot at PNG. Let's say this is like some name, save it, done. Okay. So this is how you can actually do all these analysis. And you can now, what you can do here is like have this circuit, add the non-inverting gain actually there. So what you'll do is like, let's say I use this resistor, Control C, Control V, and let's say I want to configure it as a non-inverting amplifier. So you can just add that to the circuit. So we have shown you how to configure it as a non-inverting amplifier instead of a voltage amplifier or voltage buffer. So let's skip that and just place that resistors. Okay. So you can, that's an exercise for you just to configure it. But I think, so this completes the real design about your low-pass Sallen-Key filter. Very information, very real world circuit. We are doing it. We can also then set and do some noise analysis. Click again. So we have done the 4 analysis: operating point, then AC, then transient, and then FFT, right? So you can do the like noise analysis, something like that. You see how much circuit noise is. and accordingly you can do that. So that's an exercise for you. So for now, uh, hope you found this informative video useful. You can also have the tuning, for example. uh, let's say click here, not really, here at tuned value. Here the tuned value, let's say I want to change the capacitor, and click here and then come back to your simulation window, and now look how the gain and something. So you are going for the capacitor minimum from 550 pico to 2.2 nano, maximum let's say 2.2 nano. And is there changes in the plots? Yes, let's say minimum. Look at this, you've got this little bit resonance like a ringing, and this can help you, the tuning can help you to optimize your design. So I'm using this one. Okay, so you can always do this. So KiCAD, a free software, very powerful, very useful. So hope you found this module very useful, and if you did so, click the like button, share it with others, and stay tuned for more engaging content like this. And I hope you're liking us, and give us your support with by sharing it with others for wider reach. Till then, wish you happy learning.